Back to Calculus 1, one of my favorite sections, related rates. This is applied section, which means 100% word problems. We solve problems in engineering and so on, and we make money with it. You can work as a consultant. We start by understanding the title and what it's all about. As you can see, we have word rates and we learn about derivatives. So we know that the derivative is a rate of change. And then further, that word is plurals, which means that there's s in the end, right? So that means there will be multiple rates and they will be related by an equation. Very simple. So just to understand this a little bit, before we expand on it, if I have a square and I ask of the square to double one side, well, in order to remain a square, it will have to double the other side like that, and then when you complete it, you see that you doubled each side in length, but the area quadrupled, right? So the square became 4 times larger by doubling each of the sides. We can do this with volume as well, right? You take a little cube. Let's say you take a little ice cube and you leave it on the sun and it goes, right? It loses the volume. Each side of the ice cube will shrink, and you will lose the surface area and you lose the volume. Take a spherical balloon. Take a spherical balloon, weather balloon. You can inflate, right? It becomes larger. As the balloon becomes larger, there is more volume inside, bigger surface area of the balloon, right? Larger the radius of the balloon. So you could think about the changes that are happening here in any of these objects, whether they're 2D or 3D, and write the equations. We take the derivative in respect to time to see how those aspects change in respect to time. It takes time for ice cube to melt and change its volume and change its surface area. It takes time to inflate the balloon, to change its radius and surface area and volume. So because it takes time, this change happens with time, we will be taking all of our derivatives in respect to dt, time. But then we will be talking about the volume, side, diagonal, and all of these others. So chain rule everywhere, right? Chain rule everywhere, because you are taking the derivative of volume, which is changing in respect to time, which is changing, both are variables, and then chain rule happens. So all of these concepts will work this way. So what I want to write, so now let me just finish this first, this square. So the side grew from 1 into 2, and the area grew from 1 into 4 units. Now that happens in time. So I can create a word problem out of this, because I want to see, you know, how fast things change. I already talked about the concept that you are lightest when you wake up in the morning for that particular day, and you are tallest for that particular day. As you start moving around during the day, your joints will slightly, right, shrink, and you will be fractions of an inch shorter, and you will be much heavier by the end of the day than in the morning, unless you live elsewhere. So in this case, for the square, I can say, find the relationship
or find the relationship of the change between the side and area in time. So I will write that area of the square is side squared, and because I want to learn about related rates, I will differentiate this in time because I want to see how fast is the area changing given the change in side in time. Everything that you do has to happen in time. What is the ultimate speed of limit, the speed limit for causality and information in the universe? Speed of light, exactly. So, can we have faster than speed of light? How much do you know, actually? Can we have the faster than light speed? Yes, in relative, yes. Because of the expansion of space. So there are galaxies relative to each other that are moving faster than light in opposite directions because the space expands. And you can never reach the end of the universe because of that. Because on the opposite ends, it's much faster than speed of light. You can't go faster than that. So for any individual object, speed of light is ultimate speed limit. But then if you have the relative two objects, then, and this expansion of space in between, yes, things are faster than light. There are also some theoretical particles and so on that are being researched, like tachyons and stuff, but that's it. So everything has to happen in time. And every time you look up at the stars, well, now you can't see anything, it's just you see satellites. But if you ever end up going somewhere where there's no civilization for miles around, you will actually see in the sky, you will see stars. You are looking into deep, deep past because these things are so far out there. It takes 40, 50,000 years for light to reach Earth, which means that every time you look and you see a star, you are looking at that star like 10,000 years ago, 100,000 years ago, 150,000 years ago, million years ago, and so on. Yes?
Like I read somewhere that if aliens are looking to Earth through a telescope, they would bypass the dinosaurs.
Yes.
Is it true?
Yes. Yes. So you literally have to park a spaceship next to it, and our sun is lagging 8 minutes, right? Our sun is lagging 8 minutes. So if you are to remove the sun, replace it with a Manhattan-size black hole, that's how big it needs to be in order for sun to be collapsed into a black hole, size of Manhattan. For 8 minutes, we will have no information that anything happened because the gravity would be uninterrupted because the sun and the black hole size of Manhattan produce the same gravitational field. The problem is the heat that we don't get anymore, so we die after 8 minutes because that's it. All of the radiation that sun sends for us to live and the plants to live will be on for 8 minutes because that's how long it takes to reach us. Mars, when it's close, is about half a minute lag time to 2 minutes, depending on. So if you are thinking of driving something on Mars, right? It takes, so it has a camera. It takes 30 seconds, let's say, for that information to say, there's a rock, there is a rock, there is a rock, right? There's 30 seconds delay to receive that. Then you have to go, whoa, and then that travels 30 seconds back. So it's been at least a minute, right? That thing probably crashed a long time ago, right? So you need autonomous driving. You need to go at extremely slow speeds. So when you see something, it could be 4 minutes before the reaction is made if you are driving with a joystick from Earth. So autonomous, right? So everything happens in time. And did you sign up to go to Mars? No? Yeah. Oh, I signed up. Well, that's cool.
Let's go.
No, I'm serious. I want to go home. I want to go home. I've been stuck here for years.
Right now.
What?
I'll probably sign up.
Yeah, that's good.
I'll sign up for like the science channel.
Fifth? No, the first one.
You know, the Mars rover sings happy birthday to itself every year.
Oh,
Yeah, right?
I know. But no, he's going to send 100 people. It's okay. I like it. It's going to be a party. No, yeah, the TV eludes me every time. It's just no waste time. Oh yeah, we were supposed to do this now. Okay, good. So yeah, so that was a little bit of space, a little bit of course talking about traveling. Vacation spots and so on. Now let's go back. So we were talking about the square, and we said how if you double the side, you quadruple the area. And I would like to see what is the relationship that achieves that. And then I also want to see how fast things change in regards to time. So if we take the derivative of a is 1, right? But then you have dA dt. So dA dt is equal to 2s ds dt. This is standard chain rule. Nothing special happened here. This is exactly what you learned in chain rule and implicit differentiation. Every time you are taking the derivative when variables don't match, you have to follow with ds dt, dy dt, dr dt, and so on. So I believe in a textbook they have the oil rig, the famous BP incident, right? You have the oil rig, it starts leaking, or a tanker or whatever it is, and it starts leaking oil. It's going to spread uniformly, let's say no currents there, so it's going to spread uniformly in a circular fashion, and then you wait a little bit longer, and you wait longer and longer, and the longer you wait, the wider it is, harder to clean up, right? So you have to act fast. But you can compute how fast is this spreading by knowing few facts. So you want to see what is the area that you have to clean up, and everything is charged by the area, how much area you have to clean up. So if you think about this, the area of the circle is pi r squared. The key for the entire section is for you to realize which letters are variables, are changing, and which ones are constants, not changing. In this case, pi is a constant, we all know that. And it should be clear, and it should be common sense, that as radius grows, the area grows, so both of those are variables. You will literally think about a and r as x and y. So now what's going to happen here is I will take again the derivative in time because I want to see how fast. Remember, fast, it's a speed. It's miles per hour, right? It's per hour, per time. How fast you can get somewhere per minute, per hour, per year. What's the speed of the Earth? Yes, 1 revolution per year. Very good. It goes around the sun once in a year. There you go. Well, there's a little perturbation there, right? But that's technically what it is, right? But it's again per time, right? Per year. By the way, if you want to know how fast the planet is, realize this. We have our speed limits to be average 60 miles per hour, right? Let's say, because that's 55 on that side, the 22, and on this side we have 78, 65, the average is 60, right? So let's say that 60 miles per hour is the speed that humans are comfortable with, right? Shall we? Okay, fine. So well, you also have 25 miles per hour and 30 miles, right? Zones. So okay, let's all agree on I know you drive 100. So you shouldn't, but yeah. So what I want to say is, if you take the orbit of the Earth around the Sun, the path, right, that Earth takes to go around the Sun, and you drive 60 miles per hour on that path, Earth will catch up with you and crush you 1,111 times. Yes. 1,100. So you can just multiply that by 60 and figure out what's the speed, right, in miles per hour. You can figure out what's the speed of the Earth then, but average speed of the Earth. But it's just so pathetic. Everything, what we think of a distance and a speed and so on, is just negligent. And the size, right? See a building and say, damn, it's a big building. It's nothing.
It's all relative.
Exactly. That's how puny and tiny we are. That's it.
Yeah, but at least there's like smaller things to make us feel big. Like,
Yeah, I know.
yeah.
So just imagine a species out there that can squash us that way. Like let's say a civilization type 3, for instance, the galactic one, right?
There's like the theory that like our universe is just like a science project sitting on some really shelf.
Yeah, petri dish.
Yeah.
It's like, yeah, we don't need this universe anymore. Lights out, boys. Let's make a new one. Petri dish, big bang. Spray some liquid in it. There you go. 15 billion years, right? We're dying like 80 years. We're dead. All right. What was I talking about? Yeah, this lecture is so easy to get sidetracked. Oh, yes, the oil spill. There we go. Oil spill, yes. Just same topic. Oil rig right in the middle, and it starts leaking oil. Oil is going to spread in concentric circle, or it's going to roll. If there is no current, ocean, sea, whatever it is, if there's no current, it's going to be circular, spreading in all directions equally. And obviously, all of that happens in time. I want to know how fast. Listen to the wording, because every question has this word fast. The word fast means you must take the derivative in respect to time, because that is what fast is for, in time. So, how fast is the area changing in respect to radius? How fast means I have to take the derivative in respect to time. So, d dt for the entire equation. Again. And what we get is the change in area over change in time is 2 pi r dr dt. The derivative of r squared is 2r. Pi is a constant, copy that. And then because we were taking the derivative of r with respect to t, we have dr dt as a chain rule piece because of dimensional mismatch, or whatever you want to call it. The rest is they give you the numbers. You give you the numbers, you plug in the numbers, and you compute stuff. Let's see the numbers, because they did give us numbers, I think. I think this is example. Maybe, oh no, it is example. Example 1, spreading oil. An oil rig springs a leak in calm seas, right? No current. And the oil spreads in circular patches around the rig. If the radius of the oil patch increases at the rate, such a key one. Radius increases as a rate. As soon as you see rate, you know that the piece of information they're giving you is dr dt. Because the radius is increasing at the rate of, and they also give you units. 30 miles per hour, no, meters per hour. 30 meters per hour. 30 meters per hour. So in every hour, radius is 30 meters longer. I'm 2 meters tall, almost 2 meters tall. That means 15 of my heights. 15 of my heights stacked, right? In 1 hour. How fast is the area changing? This is the way to write fast, right? I told you over dt. So how fast is the area changing if the radius is, they gave us a number, 100 meters. So if you know that basic geometry, if you are able to take the derivative, the rest is just plug and pray, right? Right now. This is, we're talking about area of the circle. This is what you write. It should be common sense. Fast. Take derivative of time. Now you employ your chain rule and implicit differentiation, all the stuff you know. This equation here is called related rates. Look. Related rates. One more time. Related rates. These two rates are related by this equation. So you have your related rates formula. Maybe I'm going to write that in here, if the pen works. It's magic. You just made an Apple comment because it's not going to go well for you. So this is related rates. That's the formula that's related rates. And all you need to do is to plug numbers in. You have the RDT, that's 30. You have this is 100. So you have 200, 6,000 pi, and you're done. Right? 6,000 pi. Yeah. So the ADT is equal to 2 times pi times R is 100, and then times the RDT, which is 30, which is 6,000 pi meters squared per hour. And remember, you are billed by meters squared, right? So if it's rising this fast, you're going to call the cleanup crew right away, not deliberate on things too long. Converging airplanes. What is the job of a tower on the airport? Is that, yeah, make sure they don't crash. That easy? Why?
There's a lot of things that can go wrong.
A lot of rates.
The rates that you gotta keep related.
This is live. If you're ever interested.
All those are.
Yeah.
So the yellow is planes where the blue.
Yeah. You see the Newark over here?
Yeah.
Newark Airport right there. Awesome.
We should be able to zoom in a little bit.
All right. So like how many?
What about JFK? Let's see if it less. No, it's actually less than Newark. Wow.
No, this didn't load. Is that a refresh? Let me try a different web browser, see if it's gonna do.
No.
Well, for some websites you actually have to. Let's see if it's gonna work better. This website is lagging so much. Here's a Sweden. Yeah. But I've never seen this actually perform well. This website is always slow. Well, no, it's loading, but it takes time. Yes. There they are. That's much better. That's how it looks like. That's the East Coast. And you untangle this. Each one of these has its own feet, its own height, and so on. And yeah, when you are summoning the tower, you don't manage this. Software manages this. You manage the software, the software can monitor this. Look at this.
So wait, if the software messes up, who do you blame?
Computer science majors that wrote the software. And I'm looking at one right there. So now we are going to take a look at a problem that deals with two airplanes, right? And then you extrapolate that 200,000 airplanes, right, that are in the air. And this is just commercial stuff that is logged. This website does not log military transports, military airplanes, fighters, and so on. And then, obviously, Obama's plane is not on the map there, but everything else. And this is real time, so you get to, click on any one of these. It gives you all the info, right, where the currently plane is and so on. And I don't know if they still. Oh, they do. I don't know if it's still free. Is it? Too bad.
What's it supposed to give you?
A camera sees what's in front of it. Aerial footage. Yeah. It's pretty boring if it's cloudy or if it's going over the sea. It's like just blue. Okay, so now let's take a look at problem that would be the base problem that you start to untangle something like this eventually. So what are we having? We're having two airplanes that are traveling towards the airport. Look at those drawing skills. Those are stick figure airplanes. So, is B the airport right there? And these two airplanes are approaching the airport. Did I start the stream? Forgot. Yes, good. Whew. All right. So we have two airplanes approaching, and they give us the two small airplanes approach an airport, one flying due west at 120 miles per hour, and the other is going due north 150 miles per hour. So how fast is the distance between them changing So how fast is the distance between them changing if the westbound plane is 180 miles away and the other is 225 miles away? So 180 and 225, and then speeds 120 and 150 miles per hour.
Use Pythagorean theorem.
Excellent. So for a problem like this, you are going to use your eyes to notice a right triangle. Once you notice the right triangle, you have few formulas that you can use for right triangle, namely 6 trigonometric functions. Sine, cosine, all of them. Do you see any angles? Are angles important? Hell no. Scrap that, right? So all 6 trig functions, we're not going to use them here. What else can we find for any triangle? Perimeter and area. Did they ask us how fast any of those change, perimeter or area? No, right? The only thing that is left is the first thing you suggested, which is Pythagorean theorem. So your list for triangle, for right triangle, is always going to be bounded by these concepts. Trig, 6 of those, area, perimeter, and Pythagorean theorem. One of those will work. You just have to think a little bit which of those components is the first equation you write. The rest is automatic. Derivative in respect to time, plug all the numbers in, done. Very systematic. But this is the first part where you actually have to read, understand the problem, draw appropriate picture if it's not given, and then figure out what is the equation from which you are going to derive the related rates that you need to solve the problem. So now you see that they want the change in distance of the hypotenuse. You have the change in distance of the legs, and you have the distance of legs. You can find, if you need, hypotenuse as well, because you have these two. You can use Pythagorean theorem for that as well. There's a lot of stuff that you can do. So let's do it. We write Pythagorean theorem. Pythagorean theorem says, we'll label this as x, label this as y. X squared plus y squared is going to be the big distance squared, which we are looking for. And then we are going to differentiate this in respect to time because we want to see how fast it changes in time. So that's going to be 2x dx dt plus 2y dy dt is equal to 2d dd dt. Observe that there is a chain rule on every piece because t is the main variable, not x, t. So you have to have dx dt, dy dt, dd dt. All of these 2's are going to cancel because you can factor a 2 on the left-hand side and then divide by 2. So if you divide area by 2, there you go. They're gone. The expression that is left is your related rates expression. You have 3 rates. So let's just do a quick check. X, I have 180. X dx dt, I have 120. Y is 225, I have that. And then this is 150. I am looking for dd dt, which means check that off because, right? The only thing I don't have is d. And d I can get from here. So we go first with the fact that d is equal to the plus minus square root of x squared plus y squared, but we don't use the minus because distances are never negative. So now this is going to be the square root of that's 180, right? Squared plus 225 squared, which is equal to something. You have to take a square root of that. So about 288. For 288? Yeah, it was obvious. And I know. And then we have the formula. So we have x, which is 180, times the dx dt, which is 120, plus y, which is 225, times 150 is equal to 288 times dd dt. All I did is I just plugged everything in. All right, so now I have to talk about something that is important for physics and it's important for these problems so we can have the correct answer. Observe what's happening with these planes. Are they getting closer to each other? Yes. So next time you measure, they're going to be maybe this far apart, and then this far apart, and this far apart, and then hopefully they're going to land one at a time. Yeah. That's the tower. We talked about it. So now, these values diminish, right? So we want to use proper signs to make sure that the physics of this, in terms of directions, so on, ends up correct. We are supposed to obtain negative answer. Why are we supposed to obtain negative answer? Because the distance is shrinking. If you want the quantity that's getting smaller, right, it's a negative quantity. So we need to get negative number. Now, thinking about this, if you put your origin 0, 0, you put your origin where the airport is, you see that the airplane on the right, that it's going westbound, is going left, which means it will have negative speed. Did this make any sense?
Yeah.
Good. And also the airplane going up, also negative. In relation to the airport. So now when you compute all of this, you will get a negative answer which you need to. Anyone has the? Well, I mean, we can do it by hand. So 12 is 3 times 2 times 2. So 3 times 18 is 54, 108, 216, and 2 zeros. Right? And then we have, and that's negative, right? And then minus 15 is 5 times 3, right? And if you multiply, the way to multiply by 5 is to multiply by 10 and then divide by 2. So you multiply by 10. Yeah, 1125. And then we have to multiply that by 3. So 3375 and a 0. That's it. Equals to 288 dd dt. These two numbers add together. You can add them forward, backward, it doesn't really matter. So that's going to be negative 5, 5, 3, 5, 0 equals to 288 dd dt. Now 288, you can also quickly come up with this because 288 is twice 144, which is 12 squared. Each one of those is 12 squared. Each one of those is 2 times 2 times 3. So you have 7 2s. No, 2 times 2, 5 2s and 2 3s. Right? This is to give me 12, 5 2s and 2 3s. So you can just divide by these. Take half, 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 and then divide 3 by 3. So what's the total? Just get lazy. What's the answer? Negative? How much? 190? 192 miles per hour. There you go. Awesome. I will leave that problem for later. All right, next problem. Really like this one.
Ready for engine chill, 30 seconds.
Prompt is ready for engine chill. Spacecraft on internal power. Stage 1 logs, stage 1 fuel, stage 2 fill rates all nominal.
By the way, are these actually actors or they're real engineers? They all look like models over there. Did you notice that?
Yeah, no, it's
Like in NASA, everyone is 70 years old.
yeah.
Look at their mission controls. Like everyone is 20s.
Prompt confirmed, ready for engine chill, 30 seconds.
Prompt is ready for engine chill.
She's 10.
Spacecraft on internal power. Stage 1 logs, stage 1 fuel, stage 2 fill rates all nominal.
The mission control is about this size.
All stations verified, ready for launch. All stations acknowledged. FTS. Prompt.
Prompt go.
ABI.
ABIs go.
GNC.
GNC go.
OSM.
go.
Recovery.
Landings go.
LCLD. Go for launch. 5, 4, 3, 2, 1. Liftoff with the Falcon 9.
Stage 1 propulsion is nominal. Stage 1 is underneath split. Stage 1 boost back is starting. Chapter 1 and 2 have been recorded. Final.
All right. Now you saw the age group that works for SpaceX. We're going to Mars with them, I guess. Those are actually their 300 workers, the ones that are cheering and jumping in the back. And you saw the mission control. So I think Elon Musk is the oldest in the whole group there. And they are our only hope now. Like, we only research that and Tesla and everything that Elon Musk actually does. So, okay, so, yeah. So now, the reason why I played that video is it was recorded, right? The launch was recorded. So what we have there during that video is you have a launch platform. I put some rocket over there. This is my design. It's top secret, so this is all you get. I'll put the logo on it as well here. It's N. There we go. So this rocket, this launch needs to be recorded, and the rocket needs to be in the center of the shot at all the time, right? All the time. The problem is there's a little bit of heat and fire, right, when the launch happens, so you can't really have someone. I mean, you could, but shouldn't. Someone with the camera right there, right, recording this. So what you do is you install a camera. This is a very high-tech camera, as you can see. You install the camera, and what you do is you put that camera, the hinge, that will be rotated by the motor, and you need to calculate the equation which you can program so that the camera can automatically, in respect to the speed of the rocket, adjust itself so that the rocket is always in the middle of the shot. So what do you have? The rocket is going to go up, vertically up. Let's call this height h, which would make the change in h, dh dt, the speed of the rocket, upwards. And let's put this, I don't know, 1,000 feet away. I don't know, whatever. Put the 1,000 feet away. So when you put this 1,000 feet away, and you want to rotate this, you are looking for the change in angle. You are looking for angular velocity, in physics known as omega. So we are after the equation that will model d theta dt, in physics known as omega. And once you know that, you can program, and then whatever the input you get from this speed, which you know at all times, it will adjust itself in a program here. It will turn the camera faster or slower. It should be common sense that camera should start moving faster and then it should slow down, right? And that input should come from these variables. So now, what geometry do you have over there? Which geometry? What's the geometry of the right triangle? That's all I'm always looking for, right triangle. There's a right angle here, right? Hopefully, you're not trying to launch it from a different country. You're trying to launch it off the planet, all right? So there is the 90 degrees, right? And we have 1,000 feet towards the camera. So you have, this is the height h. This is 1,000 feet. This distance is irrelevant because we have an angle. What concept do we use? Pythagorean theorem, perimeter. What do we use? Trig function. Exactly. Because we are trying to relate the lengths of sides to angles, right? And if we are doing that, we better use trig. Now, which sides do I have? I am avoiding hypotenuse. So what are the only two trig functions that do not have hypotenuse? Tangent and cotangent. So which one do we want to use? Obviously tangent, right? So I'm going to write. So see, that's the thought process. We were thinking out loud. It's a thought process. What geometry do I have? Right triangles. What are all the possible things that I can consider? Well, I have angles. Trig. Okay, trig. I have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Right, so you go. Right, SOHCAHTOA, yes. So which out of 6 do I pick? Well, in this case, pick one of the two because you have two lengths, which is opposite and adjacent. So it's either tangent or cotangent. Yes, you can use Pythagorean theorem, figure this one, and then use sine or cosine, but if you like pain, right? Why would you do that? So we're going to use tangent. Theta as opposite over adjacent, which means that in our case, tangent theta is equal to height divided by 1000, which is the adjacent side. Now, we are looking for the d theta dt. So clearly, we differentiate this in terms of time. What is the derivative of tangent? Well, theta. And then we have d theta dt equals to 1 over 1000 is a constant. We rewrite that. And then we have the derivative of h is dh dt. Awesome. So now this d theta dt is our omega, which we are looking for. So that needs to stay alone, which means we have to retire secant, right? Secant goes to the other side. But what's secant?
Minus 1 upon 1 plus x. Like, I mean,
Hold on. No, what's in terms of easiest formula? 1 over cosine squared, right? So if secant is 1 over cosine squared, how about we hit both sides of the equation by a cosine squared? That will kill a secant. So multiply by a cosine squared theta on both sides. And as French would say, voila. I don't know if they say it that way, but it is. So d theta dt is equal to cosine squared theta over 1000 times dh dt. This is the related rates formula for this situation. Rates. You can see that the speed at which the camera should turn is directly proportional to the angle at which it's looking at and the h dt, speed of the rocket. Now you can, figure out other stuff, but that's technically what you need. This is your job as engineer, to figure these things out. You want to be an engineer working for SpaceX or GE or whatever company, this is how your job looks like, this section in calculus. None of the nonsense we did before to find the derivatives and so on, because you have software for that, and you will rarely be doing this. As engineer, you are supposed to figure this stuff out, then you give it back and he programs this in, then another person is going to take both of those things and put them into one thing, and you send that stuff is machined, made, prototypes, so on. That's how it's done, right? So you are paid to figure this out and then make the prototype, so on, so the coding can be done and all of the other aspects of this. So as far as we are concerned, this problem is solved. Now the problem might, in addition to this, offer you the numbers, right? At 45 degrees, there's put that here, right? And the speed of the rocket was 99% the speed of light. Put that here. And you're done, right? So the rest, every time when you figure out related rates formula, the rest is just Plug the numbers in. Plug the numbers in and calculate. This portion here, and the money is in the thought process. What is my geometry? It's a right triangle. What are all of the possible formulas that I can consider? You have the list because you learned something in school. And then you eliminate one by one, right? Or you immediately no expansion, I don't care. You plug stuff in, differentiate a little bit, move the terms around because you took algebra as well, and there you go. Paycheck. Or pass every class with C, be charismatic in the interview, get hired, and then booted in 3 months because you went there, looked at the stuff, and said, "What the hell is this?" And they say, "Well, wait, you went to MIT." Yeah, I did go. It's not the fact that you're going to school. It's really what you're learning in school. That's the part. Anyone wants to go home now? Oh, no, not anymore. Yeah, we'll do another problem because you're so eager. And you're welcome. Oh. See how the outcome changes to become French quickly. Quickly. Let's design another system. So this is a conveyor belt. And here is the sand coming in, falling off the conveyor belt, and it's creating a pile. Sand, rocks, quarry, whatever. I don't care. Corn, whatever it is. I don't care what it is. Whatever stuff you start dropping down like this, it's going to go in a pile. Awesome. Now you're looking at this thing, and you know that if you wait, the cone is going to be bigger, and bigger, and bigger, and bigger. So you wait longer, cone looks like that. What changed? And the answer is everything. The height changed, the radius changed, surface area changed, volume changed, everything changed. I can't hear you, the air conditioning got a volume. Why would area be the main? It's a three-dimensional object. It's added to the sides and then slides. Okay, what do you think? Yes, so everything is changing because the longer you wait, yes. So everything grows at the same time, causing one another to grow. Technically, we get the measurement. The only measurement that I would consider is the volume, which is how much stuff do I have, right? But the surface area, surface area is there, but generally you want to know surface area if you need to paint something on it, or because, I don't know, because you can't get the weight out of the surface area, technically for design purposes, I would say, right? You meant to say what? Now we're on the same page. All right. So we're supposed to do this problem. And someone is supposed to know the volume of the cone. Right? Someone is supposed to know every single volume of a 3D shape you see. So let's learn them all in 3 equations before we continue with this problem. So we'll come back to this problem. There is this little important piece that you must know for this section, otherwise doom. We're going to have objects like box, which could be a square or whatever rectangular box. In the same category, we are going to put the cylinder. Any shapes like that. And their volume is area of the base times the height of the object. So this is the base. This is the base. So area of the base times the height of the object. Next to it, I'm going to put a pyramid and a cone. I'm going to call them spiky objects. And the volume of these guys, all of them, is going to be 1/3 area of the base times height. And in its own category, there is a sphere, a ball, whose volume is 4/3 pi r cubed. And you have no more excuses after this. So these cover any shape that you can possibly imagine. If you know how to find the area of the base, which could be a square, or a rectangle, or a circle, or a triangle, right? The three-side pyramid. If you know how to find the area of the base, you should be able to multiply by a number to get the volume, right? The height, and then 1/3 if it's a spiky object, right? So look at these two, right? Same base. That's a cylinder, that's a cone. The difference is, right, this has the same size over here, and over here is spiky. That's all. Same happens with the other one. I can have a 3-sided prism, 6-sided prism, or 4-sided prism, which is known as a box. You're sitting in one right now, right? So the volume of this room is what? Area of the floor times the height along any of the walls in the corner, or anywhere else, perpendicular. So you can find all of the volumes now. So now I'm going to ask you, what is the volume for this? Because we agreed that this over here is going to be sand dripping on a pile. Volume, right, grows as soon as that's happening. Height and radius are growing as well. So we know that, and we know that we need to write down the formula for volume, and then we will differentiate that to find how fast all of the concepts in that formula change. So let's do that. What's the volume formula now that you know all of them?
1/3.
And that's it, just 1/3. All right, good. What's the volume of this thing? Let's go. What's the base? Pi r squared, okay. And then finally times the height. Holy nightmare, like teeth pulling. Would you rather go to the dentist or sit here? So some of you would rather go to the dentist, I hear. All right. So now we're going to do the derivative in respect to time to find how fast volume changes, how fast radius changes. Now, how many variables do I have? 3 variables. 3 variables. So how do you take the derivative of the right-hand side? Left-hand side, easy. What's happening on the right? Product rule. Radius changes, height changes. Therefore, copy the first, derivative of the second, plus copy the second, derivative of the first. Awesome, huh? You gotta love it. This is the equation that you need. That's your related rates. Now, why would you want to know this? Well, you want to know how fast the volume is changing because eventually this sand pile is going to reach the conveyor belt and then it's going to start building up on it and then eventually going to break it, right? Because if you put too much weight on top, it's going to break. And it's expensive. So you design some kind of shut-off switch. After a certain time, it turns it off, right? And you don't want to put a sensor there because if you put the sensor and you're piling sand and dirt and stones and things, it's going to get dirty and yeah, and it's not going to work if you put a photo sensor that says if you reach this height over here, right, then it shuts it off. That's going to cover the sensor, it's going to shut it off when it starts or something like that. So, and you really don't want to hire someone to sit there for like, $30,000 a year, push button every 3 hours to shut it off. So you do this calculation once, right? You hire someone, do this calculation once, then someone programs it, and that's it. So that's how we automate everything. So now when you look at this, you see what are the pieces of information that you need, and you can calculate how fast the volume is changing in time. And once you have that, you can program it and then build stuff. So implementation of that is left, once you start working, but right now we want to know how to compute. Now there's a lot of variables here. 1, which is the one you're looking for. 2, 3, 4, 5. I already counted this. 5 different variables, right, at the end. So you should have 5 different numbers. And if you don't have 5 different numbers, then you better have some other relation that you can find mathematically to reduce the number of variables to whatever you're given. In this case, they give us the geometry of this one. They would say that radius is always 2 times longer than the height, or they give us some kind of proportion or something, and that would drastically reduce the number of drastically, it would drop by 2. So you would go from 5 down to 3 variables, and then you would plug numbers, and you would do the problem. So the main issue of this section for you and for every student until you figure this out is the geometry of the problem. It should be common sense that if they mention the word volume, if they mention the word area, those are the formulas you grab for. If they don't mention any of those things, well, then you will have to pick from all of the possibilities that you have. You have to pick the right one and then use it, like the ones we did for triangle. But then you saw the procedure, right? We're talking about lengths, Pythagorean theorem. We're talking about the angle, one of the trig functions, and so on. It's very systematic. Right now it looks convoluted and crazy, but eventually it gets to be better. Just try every single problem in the book, right? And they have some spicy problems there. This book was... All right. So there's a lot of variables here. I just want to draw on the board. This asks you, what's the volume of the cylinder? Base times height. Okay, can we be more specific? Pi r squared h. That's only 1/3 off. Is the derivative going to be the same? Other than the over 3? So these two formulas differ only by over 3. This one has pi, that one has pi over 3. That's the difference between the two formulas. Do they, and I still have to take the derivative in respect to time. Do they have identical derivative other than over 3? Why no?
Because we said it in the previous round function, they don't have it. At the end of the lecture, we said I mean, you won't have it.
You say you won't have it, and you just know that because it has been communicated to you. Or it has been communicated to us through you. Okay. Anyone else? Apart from that constant difference, pi to pi over 3, if you just forget about that, would derivatives for these two be the same? And the answer is no. It won't. It was communicated correctly. Now let's see why. Look at this. What am I drawing over here? Radius. It's a variable, right? Look at this one. Constant, right? You don't have the product rule here. This is a constant. So it's just the h dt. In comparison to this problem, that one is a joke. Because the derivative here, with the r being constant, they tell you that the cylinder has, it's a barrel, right, for water, oil, whatever, gasoline, and the radius is 3 feet. Let's say it's a big one, right? If the radius is 3 feet, it's 3 feet throughout, that doesn't change ever. So you might as well plug it there and have 9 pi. As a constant, that would copy, right? And then you have the h dt. So I'm just going to copy this pi r squared. That's a constant in this case. And then we have dh dt. And you have a dv dt on this side. And look at the difference between the two equations. So in this case, it's a joke. Over there, you have 5 variables. You end up with 5 variables, and you have to do a lot of jiggling, right, juggling stuff around to figure out all of the things. Where over here, you only have two variables. 1, 2. That's a constant. It's given to you, whatever it is in a problem. So this, another aspect of this lesson is figuring out which concepts change and which concepts remain the same. Related rates also in terms of the tire pressure and volume, and right, we discussed that briefly in the class, did we? The ideal gas law for your tires. So if the tire has a constant volume, right? If the tire has a constant volume, and then NR also constant, so I can solve that equation for like this, and call all of this K. You see that the pressure directly depends on the temperature. So in the summer, you want to leave pressure down because heat outside plus the friction from the road, right? So friction from the road that you always have. If there is no friction, the car doesn't stay, right? Friction is the one that makes the car go, the grip between the tire and the asphalt. If there is no friction there, which creates heat, well, that's when the car slides off, right? Which is sponsored by leaves and oil and water combinations and snow, ice, right? All of those prevent friction, and that's why the car goes off the road. So you need that friction. Creates heat, heat temperature. So more temperature, more pressure in the tire, everything else that's constant. What happens when it's too much? Right? In summer, you find those truck trailer tires all over the highways, right? They have 18
tires to worry about. So they say, check 4, we're good to go, right? I reach destination with two tires left. The rest of the truck is dragging on the pavement. So in the summer, you lower the pressure because, I mean, you don't deflate the tire halfway. You lower the pressure like 2 or 3 psi, and the heat will make up for it. In the winter, you have whatever is, given by the manufacturer because it's going to be minus 300 degrees soon, and it's going to be fine as you drive. Perfect. Again, related rates. I want to know how fast, right? So the temperature and friction will depend on how fast you're driving, how much you're covering, how long you're driving, and all that stuff. So you can do another related rates there as the change of pressure in time, as the change in temperature in time, because right now all of your tires are in the room temperature of the outside, right? Of the outside temperature. But when you start driving, they're going to start heating up. And then again, the rate at which heat up, depending on the outside temperature. Hence the difference between what you should observe if you want to be safe and keep others safe on the road. So let's just take a look now at the textbook bold titles so that we can see some of the geometries that are expected of you to know from before. In all of my infinite goodness and wisdom and everything, I gave you the formulas on how to deal with those because you really need to know those. They are not provided on exams and final exams and so on. So, there should be some study time and review, and especially the one for the sphere because it doesn't fit into any of the other ones. Expanding square. We know 2 formulas for square. It's the perimeter and an area. Shrinking square, same thing. Expanding isosceles triangle. Isosceles triangle, 2 sides are the same and the third one has different length. So expanding isosceles triangle. An isosceles triangle always has 2 right triangles in there. Shrinking isosceles triangle. Expanding circle. Again, you have the circumference, you have the area, and you also have the diameter is twice the radius. Don't forget that one, right? The diameter is twice the radius. Expanding cube. For cube, we have 6 sides. If it's cube, they're all the same. Area of each side is side squared, right? I mean, S squared. And then you have the volume as side cube, so A cube or S cube, whatever you want to use. Now you have the diagonals on each one of the sides, and you have the major diagonal that goes through the cube. That's another one that people usually don't consider. You have to derive that one. It's not something that is a well-known formula. You have a cube. And then, let's say you want this major diagonal that goes through the cube. So how is that achieved? How do you compute this one, right? Well, you can this. So it's a diagonal on the side plus one of the sides over here, right? H, and then that gives you. So you kind of figure out all of those. It's Pythagorean theorem inside the Pythagorean theorem, and you're good to go. It's a nested Pythagorean theorem. So for cube, you can have this. Now, what are the applications? You can put a little cube made out of metal into something hot. It will expand, right? You can take the ice cube and put it outside and push it into nothing. You can see how fast that happens. So expanding and shrinking cubes, shrinking circle is that, shrinking cube is that, balloon is going to be the sphere. For sphere, you have, so sphere is a ball. You have that the area is 4 pi over 3 r cubed.
And you also have a surface area of the sphere, because maybe you want to paint something on it, right? Well, this is a volume. Area is 4 pi r squared. Technically, it's a derivative of this in terms of r. It's the only one that works that way, because sphere is a special object. So that's the sphere. And then we have a problem, which is applied problem, that says piston compression. Ta-da! Right there. So this is unfortunately how our cars still work. It's sad, but that's how it works. You put inside the chamber over there, you put inside a little bit of dead animals and plants on one side and air on the other. You explode that with a little spark from the spark plug that explodes and pushes the piston up, turns the crank, and you go to somewhere wrong. That's technically, it's been good for 150 years, unfortunately still with us. And yeah, that's the technology that we call state of the art. You have to wait for something to rot on the ground for 100,000 years, and then you extract that and explode it. Melting snowball. I would much rather consider the problems of expanding the one, because as a kid I used to watch those cartoons where a villain stands here with a little snowball. I put that evil smile on him. There we go. I put some scarf. They always have scarf. Don't trust people's scarf. There you go. Look at that. Awesome. Put a house over here. And you know it's cozy inside if it has smoke coming up. But not for long. So there is your expanding sphere, right? So the volume, how fast it will pick up the volume along the way. So it's going to be dv dt. You have the volume formula for sphere. Just differentiate, and then you will be plugging the numbers. Every time they give you the numbers, feet cubed per minute. That should be common sense. They give you the units. If it's feet cubed per minute, that has to be dv dt. I don't even want to read the problem. I don't care what the rest of the problem says. Centimeters per second, that's length per time. This is either a side or the diagonal or the radius or something. I don't even look at the question. I have no clue what it is. I look at the unit. This is why general chemistry and physics are a joke. They give you a word problem and they give you units. You look at units and you know what the formula is and just plug it back. You just need to show up for exams like that. If you take courses like that. That's technically what it is. At least that's what I did. Ooh, a bug on a parabola. Bug on a parabola. All right, here's the parabola. Here's the bug. What is it doing? It's moving along the right side of the parabola. Great. Bug's here. X that out. At the rate such that the distance from the origin is increasing. The bug is walking away from the origin. This is the origin. This is the distance between the bug and the origin. And the bug wants to be here, so the distance is greater. Probably the counterpart was right there. It's like, get the hell out of here, right? That's how couples work. And at the rate, so you have 1 centimeter per minute. So this distance, d, over here, is changing 1 centimeter per minute, which means that's the dt, right there. So you have the piece of information. You have the formula. Differentiate, plug stuff in, done. Awesome. Another bug on parabola. I always love that. This book is awesome. So you have a bug on parabola on 16 and then another bug. They should name them. That would be funny. Yeah, I know. I don't know what to do here. Carl knows that. Expanding rectangle. We have the rectangle. Expanding rectangle. And then this problem. So once you think you mastered the skills, try this one. Yeah. You will learn certain things in life. Yes. No, it will just be the distance formula. The distance formula, this over here is the distance between 2 points, and you use the distance formula and you differentiate distance formula, you plug. Yeah, secant.
Oh, I think we're gonna do like low.
It's a secant, yeah. So you have, when you do the distance formula, you will have to use x and a y, but y is equal to x squared, right? Because you have the function. So it goes like this. Altitude of the jet, right? 10-degree landing off, there's your trig. Rate of a dive of a submarine, there's your trig again. Divergent paths, well, we did convergent airplanes earlier. Now you do divergent paths of 2 boats, like the same thing. Ladder against the wall, another triangle, yes. So ladder against the wall, you know what the situation is. So you have, over here you have a house, there's a gutter right there, right? Someone puts the ladder, goes up the ladder, right there to claim the gutter, right? And then someone comes here at this point, right there, and goes, well, we first put the camera stuff, YouTube and stuff, and then go there. Right, so how fast you kick this part out is how fast this part goes down. That's it. What's the concept? Pythagorean theorem, right triangle, Pythagorean theorem all over again. And when you play the game of minus signs, you will see that this one works out to be negative because it does go down.
And the tower of Pisa in Italy.
I'm sorry?
The tower in Italy.
Yeah, tower and Pisa, yeah.
And let's use that as, or it wouldn't be a right triangle, or would it be?
Yeah, or if it's a Ninja Turtle, then in that case, you're doomed. Ladder against the wall again. I love it. I love it. Why? Why put again? Why? Just leave it out. Yeah, look, right. One more time. Moving shadow pose can be scary in some cases, but I really appreciated the shadow problem once you actually try it out and see how it works and observe how the shadows change and so on as you walk around. So I learned something about baseball here, which is awesome. That's how much I know about baseball. Growing sand pile is the one we did with the cone. Draining the tank, which is the cone. Hence your project is coming up. That's the one. Drinking a soda from, hopefully, this kind of can, which is much easier problem than the other one. So you see, all of these problems are very structured. You are doomed if you don't know geometry of them, and if you can't critically think to pick what is the right geometry for the problem. Then you're doomed. But if you know those very basic formulas, you categorize them the way I showed you, base times height, spiky objects, 1/3 times base times height, and then the sphere, just memorize them, write them 50 times, right? You will be fine in terms of, this is the concept I'm using, differentiating in terms of dt. I'm not going to forget dv, dt, dr, dt, dA, dt. I have to have it everywhere. The rest is plug and chug. Actually, should I say plug and pray? It works out. The pitfall might be those minus signs that you might not get because you didn't do analysis far enough. But that doesn't scar the problem terribly. Not being careful, however, does. If you have a circle or a sphere problem and it's stated the diameter is blah, and you put that for d, obviously it's going to be wrong, right? So be careful, right? Read.
carefully. Also consider those units. So length squared per time is dA dt. Length cubed per time is dV dt. Single length, meters per second or something, is going to be dx dt or dA dt, ds dt, dr dt, whatever is the length per time. So pay attention to units. 0.5 feet per second. That's going to be either dx or dy without looking at the problem. All I look is this. I just zoom where I see division sign. Miles per hour. This is going to be again dx dt, dy dt, ds dt, dr dt, dA dt, whatever I measure for the length. That has to be the one because it's a single unit of length divided by time. And that's how I know where it goes. Looking at units. These problems are getting exponentially more interesting. We might not have the same definition for word interesting, but you really want to consider problem 46 eventually. Ooh. This is, so you solve this, and I label you a boss, okay? 52. Took me some time to figure it out, and it was a lot of fun times. So you figure this one, and I give you the sheriff badge for the class, right? I'll go to the dollar store and get a sheriff badge, and I'll put it on you. Too much blood, but we're done. That one. I figured this one for my private theater because it was awesome. Exact position where the projector and the chair should be. And it's great. They do have these lame calculators online, which was a little bit off. Not too much. 4 inches. Okay. So there's a lot of cool stuff that you guys can learn from this section. This is the last section of chapter 3. And the first serious section that you guys have to consider if you want to be engineers. It's time to stop, wanting to be something without being that thing. That's what I found is in the US, very interesting thing. A lot of people are really consumed by what they want to be rather than actually striving to be that, working hard to be that. So there you go. This is where you begin in this section. You want to be mechanical engineer, electrical engineer, or structural engineer, or civil engineer, you should devour every single problem in this section, because this is where you make money. And I will, even I'm professor, and this is live. I stand behind my words because it is live and everyone can hear. All the garbage we did so far in this class is not going to give you your paychecks and stuff, because everything we learned so far, other than analysis of graphs, limits, and so on, is done by Mathematica and other software. And as engineers, you will never, ever take derivative by hand, integral by hand. Never. But this thing, this is your job. This is how it looks like. You designing a new thing that doesn't exist, being either on your own or in a team, and thinking in this sequence. What is the geometry that I have? What are the formulas that I need? And eventually, what is that equation that governs the principle? Once you have that, you are done with your engineering, because all you need to do is to code or give to someone else to code or build the concept. That's it. Once you know how it behaves. Everything that we were able to mathematically fully explain, we understand and have. Computers and cars and things that are 100% covered by equations that are certain, right? And what are the areas that we really suck in? Medical field. It's awful, right? It's horrible. Our body is not mathematically mapped yet. There are
Well, to some extent, there are great attempts. I mean, NGIT is a leader in neuroscience and so on, right? They do neural mappings of the brain and all of this stuff. There is a lot of work being done. But think about it. There is no, it is very rudimentary right now. We don't have cures for everything. We can't fix everything, right? And that's immediately the first thing that labels it as a pathetic. That's the stage. It's better. It's better than 100,000 years ago, right? We don't have shamans walking with potions anymore. Well, actually, we do. There are doctors with medication. We just renamed that stuff. But you don't get to change a part in a human like you get to change a part in a computer. When graphics card dies in a computer, you yank that out, you put the new one in, you reboot, and you might have to install a driver. Might. And that's it. There is no recovery time. There is no, you are done in 15 minutes tops, depending on your skill. I can do it in less than 5. But we don't have that for humans, which means that that field has a lot of development, hence a lot of biomath, hence a lot of technical stuff and so on, because that was the severe, biology was severely lacking mathematics. And guess what? Biomath today, one of the scariest branches of mathematics. You go to NGIT, you will see that the research that is being done there is scary. I mean, in terms of what kind of dynamical systems and things you need. You know, you're talking the differential equation 7, right, class. If you are studying biology on the level that it's being developed today in terms of math bio, Packers has a program, NGIT has a program. A lot of the schools have programs for that. And the research that is done today, I mean, technically the research for cancer is like, you know, it's comparable to the whole planet is in darkness. Think of the surface of the Earth. And there's a light switch somewhere, and everyone just blindfoldedly doing this, walking around, hoping to hit the switch somewhere, right? That's the best way you can express the cancer research, right? The best analogy for cancer research today. Because they're trying to guess the solution. There's no mathematics. I saw the diffusion model for a cancer, and it shows, you know, how it looks like with the little 2 bumps, and you do the incision in the wrong spot, the little bumps that they're not cut off, they can spread back and so on, why it comes back. So mathematics is trying to understand it. But until there is 100% full picture of that, mathematically, there's no way you can develop.
We got a 95.3% of 10,000 human genetic code. So we have all that in a graph right now, as of August.
Yeah, but...
So now we can compare different genetic codes to a base, like...
Yeah, but what about like that 4.8%?
Yeah.
Right now, that's just...
No, that we don't have, like maybe that's like...
Well, that's because of difficulty in getting the genetic code.
Oh, no, I'm all aware.
But there is a lot more mathematics that need to build on that.
Oh, yeah,
How does the brain work?
Now we have a reference code. As of August, we have a reference code
Yeah.
that you can compare a person's specific codes to.
Yeah.
To be able to mathematically see what parts are different. Okay.
But there is a lot of development that has to be done.
Oh, yeah.
So
I mean,
when you compare how far Apple went, right, in terms of developing ideas they stole from others, to, you know.
what happens if we do, you know, genetically map 100% of the genome? Like, where do biologists go from there exactly?
Well, it's about comparing, like,
I think this is done. I'm just going to shut the stream off so we can chat, and then we